My name is James Urillo, and I was responsible for the design and implementation of the motor.
My name is Jion Ong, and I was in charge of fin design.
My name is Mirza Usmanov. I am responsible for autonomous payload integration for Team Gold's Rocket Launch.
I am King Garcia, and I was in charge of airframe design.
I'm Jacob Riley. I was responsible for nose cone design and production.
We are the UCF Rocket Launch Initiative Team Gold. As a team, we had a unique challenge when it came to communication and collaboration during the first half of the project. This was due to one of our team members being outside of the country. We were able to circumvent this issue by using programs like GroupMe, Discord, and of course Zoom. These programs allowed us to stay in touch despite having a 12-hour time difference. This time difference had a massive effect on when we can meet, since we would either have to meet in the early morning or late evening. Luckily, our advisor, Gary, was flexible and willing to meet with us at whatever time we needed. Gary was also considered our primary stakeholder since we were launching under his high-powered license. His flexibility made it easy to communicate with him, whether it was through email, the late-night Zoom meeting, or even in person. His feedback and many years of experience were extremely crucial in development and design of the rocket, as well as tackling any issues we had. We would try to implement his feedback by adapting our design to address any concerns that Gary had while trying to keep our design in line with our project's parameters.
So for our team senior design course, we've chosen the UCF Student Rocket Launch Initiative. The objectives for this project are to construct an autonomous payload mechanism, which would place a vessel with multiple half-filled spheres within the airframe of the rocket. And the rocket should also hit a target altitude of 2,000 feet, and which would be reported with an altimeter, and to successfully land the rocket to allow capability of subsequent launches. During this project, a scoring rubric was created for competition developed by our faculty advisor, and high scores would also be granted to teams who were most accurate in reaching 2,000 feet, their survivability of their rocket/payload, and the total mass that was carried.
As mentioned, one of the objectives of this project was to load the payload to the rocket autonomously. As seen in the video clip, this integration was achieved by using a rail and platform mechanism. The platform was equipped with two IR sensors that determined the stop point of the rail. The platform was driven by a DC motor and had two mounts to hold the payload. Although we have met minimum requirements regarding the integration, there were problems such as alignment between the wheels of the platform and sending the payloads to the airframe of the rocket. Issues like these were solved by repetitive testing of the mechanism. This method of payload integration could be used in large-scale projects, especially in dangerous environments for humans. For example, with the advancements in space and planet explorations, this method can be used remotely or autonomously in places such as Mars, on the Moon, or even ISS. The testing and the plans for testing will be discussed in the next slide.
The project test plan contained two things: the payload integration and the rocket launch procedure. The payload integration tested how the payload integration motor interacts with the path they will go on, the rail, how the payload container interacted with the payload integration cart, and how the payload was autonomously loaded onto the rocket. Mirziz performed around 25 tests while trying to see how each of these things would interconnect with one another. He had to take account of the physics of the payload packages, the geometry of the payload packaging with respect to the rocket airframe, and the material of the payload packaging, as the payload will also need to be launched and returned safely. The rocket launch procedure involved the launch to demonstrate all the rocket subsystems aside from the payload, the electronics bay, airframe, motor, fins, and nose cone, working together to create a launch similar to the diagram here. All the components must work together to create a successful rocket launch. Because we are dealing with a flying projectile, we cannot test this at the university directly. However, there are club-sponsored launches provided by Palm Bay, Florida that we can do this under. In our experience, we face challenges while getting our rocket components in a timely manner, limiting the chances of us being able to test our rocket. Because of this, we got our parts through other means and were able to create our rocket on time to reach our final launch date. However, we would have liked to been able to get the rocket components sooner so we could do further testing and not have anything rushed.
Our team motivation was strong early on due to a shared interest in rocketry, but once the initial excitement of being assigned a project of this magnitude subsided, the motivation to focus on our individual parts was simply to keep the team going. We each wanted to do our parts to the best of our abilities because if any one of our parts fell short, the entire project would suffer and we might not launch. While we had input and assistance from other team members when needed, each member was expected to pull their weight to propel the project as a whole. During the research and development phase, majority of our communication and meetings were conducted through Group B and Zoom. With one of our team members stuck outside the country due to COVID, collaboration became more difficult than expected, but was overcome by creating a fixed schedule allowing us to meet. This allowed more flexibility in our meeting times and also enabled us to work more efficiently.